Hello, everyone. Well, I'm very glad to have this opportunity to share a recent study in our group. And today, my topic is the mechanism of fireside corrosion deteriorating creep rupture life of Super304H in a simulated coal-fired power plant environment. First, I'd like to introduce the research background. Well, in the advanced ultra supercritical power plant, the AUSC power plant, the surface environment of boiler tubes is very complex. For example, the tubes are exposed to high temperature oxidation and the hot corrosion caused by the deposit of coal ash as well as the flowing flue gas. At the same time, the vapor pressure inside of the tubes, the self-weight, and the vibration also impose a low level of stress on the boiler tubes, especially for a very long term of exposure, as long as 10 to the power of 5 hours. Well, unfortunately, in current studies, the failure caused by stress and the failure caused by corrosion are investigated independently. So the problem is what happens when fireside corrosion and stress both exist. In fact, in our early study, when we compare the creep rupture life of Super 304H in static air and in the simulated fireside corrosion, we find that the creep rupture life can be greatly deteriorated by fireside corrosion, and it becomes more significant under lower stresses. So the objective of this study is to try to find out how fireside corrosion impact on the creep rupture behavior. So in this study, Super 304 steel was applied as the raw material, and its creep rupture life was tested in static air environment and in fireside corrosion environment respectively. Then we can achieve the creep rupture life, for example, under the stress level of 220 megapascal. And the lifetime in this environment is determined to be 546 hours in corrosion side versus 1580 hours in air condition. So that is a big reduction in creep rupture life. And then the specimens after creep fracture were investigated in terms of their surface production and the characterization in microstructural evolution in surface layer. So next we're going to talk about the results and discussion. First, we focus on the corrosion products on surface. This page we shows the surface morphology. And first, we look at the condition in air environment. We can see that the oxide scale formed in air condition is continuous and compact with some nodules and with some very small cracks. Well, on the contrary, in the fireside corrosion case, we can find the scale is detached from the substrate and we can find many cracks, and also we can see the corrosion pits forms in the bare matrix surface. And then in this page we go to the cross-sectional morphology, and in this global view we can see the oxide layer is very thin and very adhesive to the substrate. If we show more details on the surface layer, we can find the oxide layer is very compact and well attached to the substrate and even along the creep cracks, which are caused by the tensile stress during the creep test. Well, based on the mapping results by EDS, we can find the oxide scale is mainly composed of chromium-rich oxide. Well, things are quite different in the corrosion case. Well, the first important one is that if we look at the surface layer, we can see the oxide has been detached from the underlying layer, which means in this case the oxide formed on surface is less adhesive to the substrate. And also in some local areas we can find very thick and loose products forms in some local areas. And within these products, many cracks forms during the creep test. And these thick products formed in surface will decrease the load-bearing area of the specimen. And what's more important is the sulfur concentration, which we can find in the mapping result of sulfur element in the corrosion frontier, which means the corrosion process in this case is controlled by oxidation and sulfurization together. In this page, we give the XRD patterns, which include the creep rupture specimens together with the raw material. Then we can find the surface products is mainly characterized to be manganese chromium spinel oxide and the chromium-rich oxide containing iron. And the as received 304 steel is austenite, that is FCC structure. However, after the creep fracture, we can find the existence of BCC iron structure, which means the phase transformation occurs from FCC to BCC structure in both testing conditions. Well, since the phase structure has been changed after creep fracture. And then in next part, we're going to concentrate. We're going to pay more attention in the microstructure evolution in the surface layer, especially in the area where corrosion affected. And in this page, in combination with the SEM images on cross sections, together with the EBSD mappings showing the phase structure distribution and the grain structure orientation. So we're pretty sure that the dynamic recrystallization occurs in both cases, which produce a large number of refined grains with an average grain size less than 1 micron. And the thickness of the recrystallization layer in corrosion environment is apparently larger than in air condition. That is 13 micrometers versus 9 micrometers. Well, another important thing is that the mapping from EBSD scanning also proves the phase transformation from FCC structure to BCC martensite. And this is consistent to previous XRD results. To find out why this happens, we measure the chromium concentration change as a function to the depth to the surface. And then we can see that chromium is significantly depleted in the surface layer. And the thickness of the chromium depletion layer in fireside corrosion is apparently larger than that in air condition. Well, since the measured chromium depletion layer covers the layer for recrystallization, it is reasonable to consider that uh, the occurrence of dynamic recrystallization is associated with chromium depletion. And that is because the chromium loss in the surface layer help to decrease or lower the threshold of the temperature and the strain for the occurrence of recrystallization. And on the other hand, it has also been reported martensitic phase transformation is also favored by the surface chromium depletion because the martensitic phase transformation temperature point here is termed as MS temperature point can be increased by the decrease in chromium concentration in the alloy. So these facilitate the occurrence of martensitic phase transformation during the cooling process to the room temperature. So finally, the failure mechanism of Super304H steel, which is also a promising candidate for boiler tubes in AUSC power plant, can be illustrated by the following schematic. Well, for now, we are pretty sure that the fireside corrosion is going to induce the cracking and the delamination of the oxide scales formed on surface, as well as the painting in the bare metal. And from the perspective of corrosion products, the scale detachment will reduce the effective load-bearing area and also aggravates the surface damage. Well, from the perspective of microstructure evolution in the surface layer, we have confirmed that the chromium depletion leads to the grain refinement through dynamic recrystallization. And these will produce a large number of grain boundaries in the surface layer, which are negative for the high temperature deformation during the creep test. So that's why the high temperature performance has been deteriorated to a large extent. And finally, we have the following conclusions, and I will not repeat one by one.